Okay, so let me start again. So in previous lecture, we have shown that the sufficient condition, necessary and sufficient condition on a linear space, that two norms are equivalent is that A norm x1 is less than or equal to norm x2 is less than or equal to B norm x1. Okay, so this is if and only if condition. That means if the two norms are equivalent, norm 1 and norm 2 are equivalent on a linear space, then you can find two constant A greater than 0 and B greater than 0 such that this condition is satisfied. Conversely, if this condition is given, then you can show that these two norms are equivalent. So one way we have done already that if this condition is given, then the two norms are equivalent, that the topology induced by these norms are same. Now let us prove the reverse part, that is converse part. Okay, so let us prove this. Conversely, let us suppose that, okay, so now we are going to prove the convert part. That norm 1 and norm 2 are equivalent, that is generate the same topology. On X. So what you need to prove, I'm sorry for this, we prove that it is there exists A greater than 0, B greater than 0 such that A norm x1 is less than or equal to norm of x with respect to 2 is less than or equal to B times norm of x for every x in x. That is the meaning, is not it? Okay. So actually to prove this, we need a lemma. Okay. So we need a lemma. What is the lemma? So lemma says that let norm 1 and norm 2 be two norms on X. X is a linear space. Then for delta greater than 0, there exists, for delta greater than 0, we have what you have, that is B1 01 is contained in B2 0 delta if and only if norm of X with respect to 2 norm is less than or equal to norm of X with respect to 1. And this is true for every X in X. Okay. So this result will help us to prove the converse part. So let us prove the theorem, prove this lemma. So proof of lemma. Sorry for that, someone. Yeah. Okay. So we prove the reverse part. Delta. I'm sorry. Yeah. Delta into norm x1. So we have to prove this one. Suppose this is not true. So on contrary, okay. So on contrary, suppose norm of x2 is bigger than del norm x1 for some x in x. Okay. And this implies that norm of x2 divided by norm of x1 is equal to, I'm sorry, is bigger than delta. Okay. This implies that norm x2, norm of x with respect to 1 is equal to c times delta. which is of course greater than delta. कब होगा? For some c bigger than 1. Okay, for some c bigger than 1. Okay, so let me repeat the whole thing again. What we have done, that if norm 1 and norm 2 are norms on a linear space X, then norm 1 and norm 2 are equivalent if and only if there exists a greater than 0, b greater than 0, such that this condition is satisfied. That is, a norm x1 is less than or equal to norm x2, and this norm x2 is less than or equal to b norm x1. And this must be true for every x in X. Okay, this is not for a particular choice of X. This must be true for every X. So the one part we have already done, means if the condition is given, then we have shown that these two norms are equivalent. That means they generate the same topology. Okay, conversely, suppose, so now we are going to prove the converse part. Conversely, suppose that norm 1 and norm 2 generate the same topology on X. That is, they are equivalent. We need to prove that this condition is satisfied. That is, there exists a greater than 0, b greater than 0, such that this condition is satisfied. So for this, we need a simple lemma. So lemma says that whenever norm 1 and norm 2 are two norms on a linear space X, then for given any positive delta, you have B101, that is unit open unit ball in one norm, is contained in the open ball with radius delta and centered at the same thing origin. If and only if norm x2 is less than or equal to delta times norm x1, and this must be true for every x belongs to X. Okay, so one part is easy, so we are going to prove the first part. Means if the left hand side is satisfied, left hand side implies the right hand side. That means suppose that B101 is contained in B20 delta. On contrary, suppose the right hand side is not satisfied. That means there is some vector x in X such that norm x2 is bigger than del norm x1. Okay, so what we have done? So if this is true, then norm x2 by norm x1 is bigger than delta. Because x is a some fixed vector, so norm x2 is fixed, norm x1 is fixed. So you can make it, because it is bigger than delta, so you can make it equal to c times delta. For what c? C must be bigger than 1. Okay, otherwise this condition is not satisfied. So you can choose a suitable c bigger than 1 such that norm x2 by norm x1 is c into delta. Okay, c is greater than 1. Okay, so now go to the next page. So what this c will play? So c will play the important role. Means, okay, so we are here. Fine. So what we are going to do? So we just take this one. Okay, so let us suppose that let y is x upon norm x1. Okay, then using the property of norm, you know that norm of y2 is c times delta, is not it? C into delta, because norm x2 will be above and divided by norm x1. Is it okay? So this is c into delta, and this implies that norm of y by c with respect to 2 norm is equal to 1 by c into norm of y2 by the scalar property. So this is nothing but 1 by c into c delta. So this is just delta. So what you see? You see that this y by c does not belongs to the ball centered at 0 and radius delta under 2 norm, because y by c has norm delta. So because it's an open ball, so it must be less than delta, is not it? It must be less than delta. So that's why this is a problem. On the other hand, but what you see? Norm of y by c with respect to 1 norm, it will be 1 by c. Check that, is not it? So norm y divided by c. So 1 by c, norm x1 will cancel out. So 1 by c. And because c is bigger than 1, so this quantity must be less than 1. And therefore, this implies that y by c belongs to B101. Okay. So this is a contradiction. because already we are considering, what we considering, that the one ball is contained in two ball, right? So here we proved that y by c belongs to B101, but y by c does not belong to B20 delta. So this is a contradiction. So this is a contradiction. And therefore we must have the result. Okay? And therefore we must have this result. Fine? Okay. Hence, what we have shown. Hence, norm x2 is less than or equal to delta norm x1. Okay? Converse part is easy. Converse part is easy. Means if you consider this is satisfied, then automatically you can prove that this open ball is contained in this open ball. Okay? So converse is easy. Prove it. This is an exercise for you. आप इसको prove करिए. Okay? In fact, okay, so indeed we can prove. Indeed, we can prove that this B1 0 delta 1 is a subset of B2 0 delta 2 if and only if norm x with respect to 2 is less than or equal to delta 2 by delta 1 norm of x with respect to 1 for every x in x. Okay, that is norm x2 is less than or equal to b norm x1 where b is delta 2 by delta 1 bigger than 0, right? So now you see this delta 2 by delta 1. Okay, this delta 2 by delta 1, let me write this. So this is delta 2 by delta 1, which is of course bigger than 0, is not it? Which is of course bigger than 0. I'm sorry, the reverse part also holds. So I think you have problem here. So this is not a problem. In fact, if you take the common delta 1, right? In fact, if you take common delta 1, then this one, right? So this one. So actually now proof of the theorem. Okay, so let us prove the theorem. So proof of theorem, the result, right? So what is the proof? Let norm 1, I'm sorry, okay, so I hope up to you it is clear. Indeed, if B1 0 delta 1 is contained in B2 0 delta 2, if and only if x2 is less than or equal to del 2 by delta 1 norm x1. Means what we have made the change? We have made the change here. In place of 1, we have taken delta 1. So you can verify that this is justified, because if you take delta 1 common here, then divide by delta 1 becomes here delta 2 by delta 1, and so this way. Okay, so you can see, you can visualize this one, you can prove this. Okay, it's not so difficult task. Okay, so I am taking here b so that it looks like as the b appears in our theorem. And of course this does not depend on a particular x, it is true for every x. Okay, so now proof of the theorem. Theorem means which we have considered the converse part to prove the converse part. So let norm 1 and norm 2 generate the same topology. Generate the same topology. Okay, then This implies there exists delta 1 comma delta 2 bigger than 0 and r1 comma r2 bigger than 0 such that the open ball in one norm with center 0 and radius delta 1 is contained in B2 0 delta 2. In fact, every open ball in norm 1 is also open in norm 2, and every open ball in norm 2 is also some open ball in norm 1. Okay, meaning is that if norm 1 and norm 2 generate the same topology, then whatever the open ball you consider in one norm contains some open ball in two norm. So suppose now you consider here B10 delta. So B10 delta is an open ball which is an open set with center 0 and radius r1. And because it is open set in two norm, so corresponding to 0 there must be open ball, isn't it? If O is open set, then corresponding to each point in O, you have some open ball contained entirely in the set. So likewise, because B1 is open in two norm, to be open in two norm, you must have an open ball which is entirely contained in B1. So you have a open ball in two norm which is entirely in this one. Similarly, here also, you see that the open ball in two norm contains an open ball in one norm. So this must be true if they generate the same topology. That is the meaning. Okay, fine. So this implies that by the lemma, what the lemma was, you already proved that. So by lemma, norm x2 is less than or equal to b times norm x1, right? Where b is nothing but delta 2 by delta 1. And here norm of x with respect to one norm is less than or equal to 1 by a norm x with respect to two norm, where 1 by a is 1 by a is equal to r1 by r2. So what you shown that there exists a bigger than 0, b bigger than 0 such that a norm of x with respect to 1 is less than or equal to with respect to two norm is less than or equal to b with respect to again one norm for every x in x. And this completes the proof of this theorem. Okay, so I hope it is clear to everyone. Okay, in general this is not true in a metric space. That's mean on a set, if you define two metrics, then they may be equivalent, but this condition did not be satisfied. You go to the book of S. Pannuswamy, okay, the foundations of spaces, that on a set if you define two metrics, then they may be equivalent without satisfying this condition. That is, this condition is not the necessary, this is the sufficient condition in case of the metric space. Okay, all right, let us prove the next result, which is very important. In previous lecture I have promised you that I will prove the day after tomorrow or the today I will prove. Okay, fine. So what was that result? Let us go to that page. Fine. Okay. Yeah. So what was that result? So using that result, we have proved that on a finite dimensional linear space, any two norms are equivalent, isn't it? So that is the power of that result. So using that result, we have proved this. So let us go to prove the important result. What is that? Okay. So the important result says that in the form of a lemma. What was that lemma? Lemma is like this. Let us suppose this x1, x2 dot dot xn be a linearly independent set of n vectors in a norm linear space X norm. Let us say. So X comma norm is a norm linear space. X1, X2, Xn are n linearly independent vectors. Then there exists there exists a constant C bigger than 0 such that whatever scalar you take for every choice of scalars alpha 1, alpha 2, dot 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 alpha n, we have what you have? You have that norm alpha 1 x1 plus alpha 2 x2 plus dot dot alpha n xn norm is always bigger than or equal to C times mod alpha 1 plus dot dot mod alpha n. Okay, mod alpha n. Okay, so mod alpha n. So this is the result. So let's call this is an equation 1. Okay, so now we prove this result because using this result we have proved that on a finite dimensional linear space any two norms are equivalent. That is a very important result. So because that result was proved using this lemma, so this lemma in itself is very important. So it looks very simple. Whatever linearly independent set of vectors you consider, n vectors, there exists a constant C bigger than 0. Means this C only depends on this choice of vectors, not the choice of scalars. See, for every choice of scalars, means whatever scalar you consider, you have this. Okay. So this is important. So what we are going to prove? So proof of the result. So proof of this lemma. Okay. So what is the lemma? Actually, we are going to write, let us write S is equal to mod alpha 1 plus mod alpha 2 plus dot 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 mod alpha n. Okay. So in writing in this way, if suppose this sum is 0, means all the scalars are 0, then clearly all alpha is are 0, right? Alpha j's are 0. And in this case, 1 is true. 1 is true for all C, in fact. Okay. So we now take S is bigger than 0. And in this case, first can be written as how? That is norm alpha 1 by S x1 plus alpha 2 by S x2 plus dot 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 alpha n by S xn norm is bigger than or equal to C. In more simpler way, you can write beta 1 x1 plus beta 2 x2 plus dot dot beta n xn is bigger than or equal to C. Here, what is beta j? Beta j is alpha j by S. Hence, okay, so what is need to prove? See, if S is 0, if all the scalars are 0, then nothing to prove. Whatever C you take, it is already true. Okay. So if the scalars are non-zero, suppose one of the scalar is non-zero, right? then the sum S is not 0. And in this way, in this case, we can write the above one like this, that is alpha 1 by S, alpha 2 by S, in more simpler way. That is norm of beta 1 x1, beta 2 x2, and so on, beta n xn must be bigger than or equal to C. C is constant, and that depends on x1, x2, xn, does not depends on beta 1, beta 2, beta. Where beta j is this one. So to prove that this is true, we must prove that this quantity, that is which quantity? This quantity, beta 1, x1, beta 2, x2, norm of this cannot come arbitrarily close to 0. Meaning is that, see, here, if you look at this, so this is the positive number 0, okay? This is 0, and C is somewhere here. C is bigger than 0. This is a constant. Meaning is that this beta 1, x1, beta 2, x2, dot dot beta and xn, norm of this quantity cannot cross this, okay? Cannot cross this. Always the beta 1, x1, beta 2, x2, beta and xn will be here, because that is bigger than or equal to. So this is the norm of beta j xj, okay? This is summation. This is the summation, okay? Beta j xj with norm. So this will be always bigger than C. So C is the barrier. After C, you will get this quantity. So it is enough to prove that this quantity cannot come arbitrarily close to 0. Means if you say choosing beta j, it is here. Then again choosing some beta j, you are here. Then again choosing beta j, you are here. Then again choosing beta j, you are here. Means you are coming close to 0. Means you can construct a sequence of vectors like this, okay? Vectors like this, which is converging to 0. So you might get some contradiction. You must get some contradiction. And which proves that you cannot come arbitrarily close to 0. You understand the theme? What we are going to do? We have to prove that there is a barrier C such that whatever beta j's you consider, of course, satisfying beta j's, right? Beta j is equal to alpha j by S. If you sum up this, this is 1. Such that this cannot come arbitrarily close to 0. Okay? Let me repeat again what I am saying. I am saying that C positive greater than 0 is a constant. It is a barrier such that whatever the scalars beta 1, beta 2, beta n you consider, this vector has the norm bigger than C, that it cannot cross C left side, that is cannot be less than C. Okay, so suppose this is not true, this is not bigger than C. What does it mean? It means you can always make the number closer to 0. You can take beta j such that it is here. Again, you can take beta j such that it is here. In this way, you have a sequence which converges to 0. And if you can construct a sequence which converges to 0, you will get a contradiction, which will prove that you cannot cross this C. Okay, fine. So let us do this. Okay, fine. So this is a rough idea. Okay. So what we are going to do? Hence, it is sufficient to show that the norm of beta 1 x1 plus beta 2 x2 plus dot dot beta n xn cannot come arbitrarily close to 0. Where beta j satisfies, okay, where summation beta j Here summation j is equal to 1 to n mod of beta j is 1, isn't it? You check that. Beta 1 is alpha j by s, beta j is alpha j by s, so mod alpha j by s, so mod alpha 1, mod alpha 2, mod alpha n divided by s means mod alpha 1, mod alpha 2, mod alpha n, so this is 1. Okay, so if these were false, okay, cannot come arbitrarily close to 0. So we are claiming that it cannot come arbitrarily close to 0. Suppose this is false, okay, suppose these were false, then we could choose a sequence of vectors y1, y2, dot dot ym, and so on, such that each expressible in the form, okay, sorry, many pages here. Okay, yeah, fine. Where each expressible in the form ym is equal to beta 1m. Oh, mistake I made here. Sorry, I have to take the next page first. Yeah, here. Yeah. So what is that? That is, yes, that is each ym is expressible in the form beta 1 corresponding to m x1 plus beta 2 corresponding to m x2 plus dot dot beta n corresponding to m xn, where summation beta j corresponding to m okay, j is equal to here 1 to n is again this is sum, mod of this is 1. Okay, so such that how it is, such that norm of ym converges to 0 as m tends to infinity. Okay, so this is fine. Let me repeat again what we have done, because it's very important. Okay, because it is very important. So what is the proof of lemma? Let me repeat again. So the result is that if alpha 1, alpha 2, alpha n are x1, x2, xn are linearly independent vectors in any non-linear space, then you can find a vector constant c greater than 0, such that whatever the choice of scalars you consider alpha 1, alpha 2, alpha n, you have this one. So after simplifying, if the sum is not 0, you can write in this way, that is norm beta 1 x1 plus beta 2 x2 dot dot beta n xn is bigger than or equal to c, where c is a constant. So if you cannot cross this one, okay, meaning is that if this is bigger than or equal to c, right, suppose it is not true, means it cannot come arbitrarily close to 0. Okay, so the meaning is that there is a barrier c, you cannot cross c. That means this sum cannot come arbitrarily close to 0. And suppose this is false, means this is not true, means you can come arbitrarily close to 0. Means you can construct a sequence of vectors choosing beta 1, beta 2, beta n different, that is y1, y2, ym, which converges to 0. What is ym? Ym is this one. Ym means each expressible in that form, that is beta j xj plus beta 2 x2 plus beta n xn. So summation beta j x j type. So corresponding to 1, you have beta 1 1, beta 2 1, beta n 1. Corresponding to y2 2, you have this one. So you can construct a sequence of vectors y1 y2 yn where each scalar satisfies this condition such that norm ym converges to 0. So let us see what is going to happen. That is what we are getting contradiction. What contradiction we will get that. Okay. So here we are. Okay. Now, since this is important fact, since summation j is equal to 1 to n mod of beta j corresponding to m is 1, what does it imply? We have mod of beta j corresponding to m is less than or equal to 1, right? For all j, of course, j lies between 1 to n, right? Hence, the sequence, what the sequence? Beta jm corresponding to m is equal to 1 to infinity equal to beta j1 comma beta j2 comma and so on beta jm comma dot 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 is a bounded. This is a bounded sequence. And if it is a bounded sequence, then you know by the Bolzano-Weierstrass theorem it has a convergent subsequence. So by Bolzano-Weierstrass theorem, Bolzano-Weierstrass theorem, beta 1 m is equal to 1 to infinity has a convergent subsequence. Okay, let beta 1 be the limit of that subsequence, and let y1m m is equal to 1 to infinity, sorry, and let y1m m is equal to 1 to infinity be the corresponding subsequence of ym, that is actually here y1m is gamma 1m x1 plus, for your understanding I am writing here, plus beta 2 corresponding to m x2 plus and so on beta n m xn, okay, such that this summation j is equal to 2 to n mod beta j m plus mod of gamma 1 m is 1, right? And this gamma 1 m converges to beta 1 because that gamma 1 is a subsequence of beta 1 m. Okay, this gamma 1 m is a subsequence of beta 1 m and converges to beta 1 as m goes to infinity. Okay, so I hope up to here it is clear. So by the same argument, okay, and you have the subsequence y1m is like this. This is y1m. So y1m means you have this one, gamma 1m x1 plus beta 2. So beta 2, and similarly in the next argument, by the similar argument in next step, beta 2m has a subsequence. In the next step, beta 3m has a subsequence, and ynm will have the subsequence y2m, and so on. Okay, so go to the next page. By the same argument, y1m yeah, y1m m is equal to 1 to infinity has a subsequence y2m, m is equal to 1 to infinity. Okay, this is y2m has a subsequence for which the corresponding subsequence I want to finish it. Okay, you just stay here. Subsequence of sequence beta 2m, m is equal to 1 to infinity, converges to beta 2. Okay, continuing this process. Okay, so continuing this process, after n steps, we obtain a subsequence ynm, m is equal to 1 to infinity, yn1 comma yn2 comma dot dot ynm comma dot 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 of m is equal to 1 to infinity, whose terms are of the form. What is the form? Of the form like this. Okay, ynm is equal to summation k is equal to 1 to n gamma k corresponding to m x k, where the summation k is equal to 1 to n mod of gamma k corresponding to m is 1. With scalars, with gamma k satisfying, because these are the subsequences of beta 1, beta 2, beta m, right? Gamma k m converges to beta k as m tends to infinity. Okay, as m tends to infinity. Hence, what you see, as m goes to infinity, this ynm converges to y is equal to some vector. What is the vector? Because as m tends to infinity, gamma 1m becomes beta 1, gamma 2m becomes gamma 2. So this becomes the summation k is equal to 1 to n beta k x k, and we are calling this as the vector y. Okay, so we are calling this as the vector y. Fine, this is the vector y. Okay. Okay. So here again, where the summation k is equal to 1 to n mod beta k is equal to 1, right? Because always summation k is equal to 1 to n mod gamma km is 1. So in the limiting case, right hand side is always 1. The left hand side will be summation of mod beta k, is not it? You look at here actually. Okay. You look at here, this one. Fine. So if you look at here, then this quantity is actually equal to 1. So right hand, if you take m tends to infinity, the right hand side is 1 and the left hand side will be beta 1, beta 2, beta n. So that's why this. Okay. So that's why this is happening. Right. Okay. So clearly, what is clear? All beta k is equal to 1 to n cannot be 0. Because this summation is 1, this summation is 1, that means at least one of the beta k is not 0. So clearly all beta k cannot be 0. The meaning is that at least one is non-zero. If at least one is non-zero, then what about this vector? Because xk are linearly independent. Okay, so we must write this. Since x1, x2, dot dot dot, xn is a linearly independent set. So we must have y is non-zero. Why? Why non-zero? Because if y is 0, you know y is 0 means summation k is equal to 1 to n beta k xk is 0. And x1, x2, xn are linearly independent. This implies that all the scalars are 0. But already you said that all the scalars cannot be 0. So the only possibility is that y is not 0. On the other hand, if you consider y and m, so y and m converges to y, is not it? Implies that norm of y and m converges to norm y as m tends to infinity. Okay. Since already you have considered, since norm of ym converges to 0, so by assumption, this is by assumption, is not it? This is not new. This is by assumption. Since norm ym converges to 0 by assumption, and this y and m is a subsequence of ym, we have norm of y and m must converge to 0. I'm sorry, must converge to 0. Okay. So this must converge to 0. Why? See, if any sequence converges to 0, then its subsequence also converges to 0. Is not it? Because ym is a sequence which norm ym is a sequence of non-negative real numbers. It converges to 0. Norm ynm is a subsequence of that sequence. So obviously it converges to 0. Is not it? So this is the result. If a subsequence converges to somewhere, you cannot guarantee that the sequence will converge at that point. But if the sequence is convergent, then whatever the subsequence you consider, it must converge to that point. So it is also 0. And you know that, hence, what you have? Hence, okay. Hence, I'm writing here. Hence, norm of y is 0. Why norm of y is 0? Because already you have shown that, what you have shown? You have shown that y and m converges to, you have shown that y and m converges to y, norm y. And here you have shown that norm y and m converges to 0. So limits cannot be different. If you have a convergent sequence, The limits cannot be different. Here you have norm y, here you have 0. So hence norm y is 0. And you know, because it's a norm, this implies that y is equal to 0. This contradicts y not equal to 0, right? So let me write this. So contradicting that, y is not 0. This establishes the result, okay? And the lemma is established. So today we are done, okay?